Hey everybody, Zachariah J here, IVC Precalc Chapter 5 Exam Review. Just wanted to remind everybody, I am not the teacher of this class. I am just a student in the class making this video to help my fellow students and just help myself understand how to do the problems or just get some practice doing the problems. So, as always, you should practice these on your own. If you get stuck on a particular problem, you can come to this video and fast forward to the problem you're having trouble on, see how I solve it, and hopefully that'll help you. Other than that, let's see if we can get started here. Start with number one. Okay, so for number one, we have to find the domain of the composite function f of g. So first we look at the function g, and we see that x cannot equal 7, otherwise that would make that undefined. And since we're putting g inside of f, we see that if x equals 0, that would make that undefined. So we have to see if the function g, what would make that whole function equal 0. So we set it to 0, 7 over x minus 7. Now we take x minus 7 times 0, and that turns out to be 0 equals what's left over is 7. Well, that can't happen, so we can never make this function equal 0. So, oops, didn't mean to erase that. There we go. So we don't have to worry about this not being part of the function or the domain. So our domain is x such that x cannot equal 7. This is set builder notation. So if you want to write an interval notation, you would write, oops, hang on, negative, that's terrible infinity. Negative infinity to 7, and then union 7 to infinity. So that just shows that 7's not part of it. So either one of these separately answers the question. You could use both, but you only need one of them. Same thing for number 2. We are going to put g inside of f. So uh, g, x cannot equal -3, otherwise that would be undefined. And for f, x cannot equal -1, or that would be undefined. So we'll take the -1, we'll set the function g to equal -1, and we will solve for x, if it's possible, which in this case it is because it's not equal to 0. So we have negative times the quantity x plus 3 is equal to 2. We're going to distribute that negative across, so we get x minus 3 equals 2. We add 3 to both sides. We're going to get x equals 5. So the function cannot actually equal this. So x, oh, I'm sorry, I got to distribute the, or move the negative as well. So the function cannot equal -5, otherwise it would make the function f 0. So x such that x cannot equal the -3, and it cannot equal the -5. It's -5 over here. So again, this is set builder notation. If you wanted to, you can of course use interval notation, which would be negative infinity to -5, and then union -5 to -3, and then union, and then -3 to infinity. So a little bit longer on this one, but there is your answer for number 2. Now let's move on to number 3. So here we got a little bit of a trickier one. We look at G, we're going to put G inside of F again. But G is basically, the domain is all real numbers. We don't have it as an irrational or as a fraction, right? So you can put anything in there and you will get a value. However, when you put that inside of here, you can't get it to be less than 0. If you make it less than 0, you're going to have an imaginary number, right? So x has to be greater than or equal to 0. So we set the function g to equal 0 to find out what that value would be. So 2x equals minus 10, x equals negative 10 divided by 2 is going to be negative 5. So that's what makes this function 0. And we can't get any lower than that. So in our set builder notation, we would write it x such that x is greater than or equal to negative 5. Because if it's equal to negative 5, that would make the function f of x 0. And that's not imaginary. If you write it in the other notation, it would be a bracket because it equals 5 is included, right? So interval notation, negative 5 to infinity. All right, number 4. I hope this one's on the test because this one's like a free, whoa, this is free points right here. Use a graph of the given one-to-one function to sketch the graph of the inverse function. For convenience, they put this blue line here for us to show you what we're reflecting around. So really, we just need to look at these 4 points, which is 1, 4, 0, 2, negative 2, 1, and negative 4, and negative 2. So to find the inverse, we basically just switch the x and the y values around. So for 1, 4, we just switch it to be 4, 1. I'll use this blue here. So this one switches to 4, 1. So let's plot the old 4, 1. That's right there. And then 0, 2 would switch to be 2, 0. Excuse me. So that would be right here. And then negative 2, 1, we'd switch that around to be 1, negative 2. So there. This pencil keeps wanting to switch to the eraser. There we go. So that's the 1, negative 2. So that dot is right here, or point rather. And then of course, negative 4, negative 2 is going to switch to negative 2, negative 4. I really should have written all of these over here, but kind of confusing just throwing the points everywhere. But we connect the dots, and this blue line, I'll write the 4, 1, and I'll write the 2, 0 here, and get rid of these guys. But this blue line is the actual inverse of the original line. So super easy, just switching those x's around. The function f is 1-to-1. Find its inverse. Okay, so to find the inverse of this, it's pretty easy. We just change all the x's to y's. So we're going to swap x for y, and then we will solve for y. So basically we'll just rewrite this as 9y minus 8 over 3y minus 8. And that of course equals x. And then we're going to solve for y. So first thing we're going to do is we're going to move that 3y minus 8 onto the other side. So that's going to mean it's x times that quantity. So x times the quantity 3y minus 8. Now we're going to distribute that 3 or that x, excuse me. So we'll get 3xy minus 8x. And of course this side is still the same because we haven't done anything with that. But next we are going to, yeah, I just distributed that. That's the only change I made here. Could have done other things in my head, but I'm trying to show you all the steps. So let's move the 9y over. So we're going to subtract 9y. So negative 8 equals 3xy minus 9y. And then, of course, we still have the minus 8x over here. Now, what we can see is the 3xy minus 9y. We can suck the y out of there. So let's do that. So we have y times the quantity 3x minus 9, that quantity, and then minus 8x. Now what we can do is we can add 8x to both sides. So we will end up with 8x minus 8. equals y times the quantity 3x minus 9. Now we will divide both sides by that 3x minus 9. So we have 8x minus 8 equals y, and then the 8x minus 8 is over 3x minus 9, and that all equals y. So there you go. There is our function inverse of x equals 8x minus 8 over 3x minus 9. Use transformations to graph the function. Determine the domain, range, and horizontal asymptote for the function. Oh boy. So this one's pretty exciting. So we got -2 with an exponent of x plus 3 plus 4. So we know that this is normally it would be an exponential curve. It would be going up like this. But since we have a negative out front, we reflect it over the x-axis. So we should have some sort of curve that looks like this going down. And since we have this plus 4, that means this point, or this line, actually 0, is going to be moved up 4. So the whole uh, graph will actually move up 4. So I'm just going to write the horizontal asymptote as y equals 4. First off, let's get this a little bit more on the grid paper. Oh crap, I didn't get the vertical line. Hang on a second. I thought I got all this stuff lined up for us, so I wouldn't be doing all this editing while trying to do the problems, but clearly I missed this one. All right, so we know that this arc is going to be somewhat going down. It's not cooperating with me. But the asymptote is at y equals 4. So I'm just going to draw this y equals 4 asymptote here. So it's not going to be infinitely close to the 0 or y equals 0. It's now going to be infinitely close to y equals 4. So now what we need to do is just to figure out kind of a little bit more approximately where the graph is going to be. We can just do the trial and error. Better write this down. So we're supposed to find the horizontal asymptote, and that is y equals 4. So let's put in a -3 into our original equation, because that's going to make the exponent 0. So -3 plus 3, and then the plus 4. So that makes it 0. So this all becomes 1. So it's -1 plus 4 equals, and that's 3, of course. So one of our points is going to be -3, 3. Whoa. All right, so let's try another value. Let's put 0 in here. So -2 with an exponent of 0 plus 3, and then all of that plus 4. So that's -2 to the third plus 4. So that's 8. So it's -8 plus 4. And that, of course, equals -4. So 0 will get us a -4y component. Let's try -1 just for fun. We'll get a third point. So we have -2 with an exponent -1 plus 3, all that plus 4. And so that's going to be -4 plus 4, and that's going to equal 0. So that's going to be our intercept there. So let's go ahead and plot these 3 points. I mean, we really only need 2 because we're just getting a rough sketch of this graph. But I put 3 of them up here for fun. So you don't really have to know too much about this negative, reflection and all that kind of stuff. If you just do the trial and error thing, if you know where the horizontal asymptote comes from, do the trial and error by plug and chugging, you're going to know that this graph turns out, gosh, this thing is not working with me, that the graph turns out pointing down, and it goes from -infinity to infinity for the domain, and our range is -infinity up to 4, but not including 4. So that's our range on that one. Here, you notice that we don't have this like plus or minus anything over here. So that's going to mean our horizontal asymptote is y equals 0. So, and a standard graph, it's going to arc up. So, and there's no reflection in front of this. So we know that this is going to be coming from negative infinity and gradually get exponentially bigger. So it's going to be an arc going up. So here's my horizontal asymptote. And we're going to do another XY chart. This triangle thing, what the heck? All right, here we go. So let's try 4. So we'll put 4 because that's going to make our exponent 0. So 5 to the 4 minus 4 really is going to become 5 to the 0. And any exponent or any number with an exponent 0 is equal to 1, right? So that's 0. So this is going to equal 1. So 4 is going to give us 1. That's 1 point. Let's try another point. Let's try 5. 5 to the exponent of 5 minus 4. And that's going to equal 5 because 5 minus 4 is 1. So 5 to the exponent of 1 is, we don't write it that way, but there you go. It's 5. So 5, 5. So let's just plot these 2 points. We'll go to 4, 1. Whoa, this is not on the line either. What the heck? Okay, that's a little better. So now we can represent our 4, 1, which is right there. And then we've got 5, 5 here. So we can see that this is going to be a pretty steep and dramatic curve here. But there you go. There is number 7 graphed. Range is negative infinity to infinity, and the domain, and then the range would be 0 not included to infinity. The next one, the function f is 1 to 1. Find its inverse. All right, so we've got x has to be greater than or equal to 0 here. So let's do 5y squared plus 3 equals x, because I need to just substitute x for y and then solve for y, right? So 5y squared equals x minus 3. And then I'm going to divide both sides by 5. So then I'll have x minus 3 divided by 5. And then that means I'm going to have y equals plus or minus the square root of x minus 3 over 5. However, in the beginning, we said that this x has to be greater than or equal to 0. So we are only going to use the positive part of this. So the inverse function of x is equal to the square root of x minus 3 over 5. The positive version of this, not the negative. All right, so we'll move on to number 9. And here we're just going to, again, sub y in for x and then solve for y. So we have y cubed minus 6 equals x. So add 6 to both sides, y cubed equals x plus 6. And then we will have the cube root of x plus 6. So the inverse function is always going to be positive for a cube root. So inverse function of x is going to equal the cube root of x plus 6. So there you go for that guy. On to number 10. All right, so for these next couple, we are going to find these 4 things: the domain of the function, the range of the function, the domain of the inverse, and the range of the inverse. So let's start with the function and find the domain. Well, first we can see that it can't be all real numbers because we have a fraction. And if we set the bottom to equal 0, that would make it undefined. So let's find out what makes this undefined. It's going to be 5/8. but here are the steps. We're going to basically add 5 and then divide by 8. So there you go, 5/8. Can't equal that. So that's our domain. It is going to be x such that x cannot equal 5/8. And then um, let's set the whole equation to equal 0. Well, 8x minus 5 times 0 is going to be 0. So 0 equals 1. Can't happen. So our range is everything except for y cannot equal 0. Kind of like our little horizontal hole there, I guess. So there you go. Now, the next two parts of this question is basically asking you to find the domain and range of the inverse function. Well, we just swap what we have for the function x, and the inverse function of x would mean the domain is actually x such that x cannot equal 0, which was the range from the original function, except for with y's. So we substitute the y's and the x. We're just switching the y's and x's around. And the same is true for the range for the inverse function of x. So write down range here, and then we are going to take the domain from above and substitute y in there. So y such that y cannot equal 5/8. So there you have it. You can see these are basically just put in the swapping them around kind of. So on to number 11. Number 11 is the exact same process where we are going to find the domain of this. Well, 2x minus 1 has to be greater than 0, otherwise we get imaginary numbers. So 2x is greater than 1, and then x is greater than 1/2. So that's our domain, is x has to be greater than 1/2. If anything smaller, you're going to get a negative number, which will be an imaginary number under the radical. So we've got function x, domain and range. All right, our domain is x such that x is greater than 1/2. And our range again is going to be y such that y is greater than 0. There you go. Now, the inverse function is basically just swapping the domain and the range around and switching out the x's and y's. So the inverse function domain is basically the range of the previous one, except for putting x. So x such that x is greater than 0. And the inverse function range, I guess I should put my x's in here. So there we go. This is x. So inverse function of x's range will be the domain of the original one, except for subbing in y's. So y such that y is greater than 1/2. And that is the answer for that question. And moving on to number 12. All right, use transformations to graph the function. Determine the domain, the range, and the horizontal asymptote. Well, we talked about this just a little bit ago. The function would normally swoop up just like this, except we've got all these transformations that we've done to it, right? We've got this +3, we've got the exponent's got a negative in it. So those things all mean something, right? So the +3 means that that graph, what we suspect it to be that exponentially growing up thing, is going to move up, right? So this is going to be our horizontal asymptote. It's going to change from y equals 0 to y equals 3. So it's moved up 3 positions. So I'll just draw this in blue here. It's this guy right here. So our graph is going to be above this line. Whoops. Did not want to erase that. All right. So this is what our graph would look like. However, we still have this negative exponent bit here, so we know that that means it's going to reflect it over the y-axis. So that means we're going to have some sort of line, something like this. That's what we suspect we should have. But let's test it out. So we'll do a little side work here. We'll do do an XY chart, and let's start with 0 because that'll make 5, 1. That's uh, just going to make it easy for us. So let's put 0 here. So 5 to the negative 0, well, plus 3, that becomes 1. So 1 plus 3, that is 4. So input of 0 gives us 4. Let's do one more. We'll do negative 1. So 5 to the negative of negative 1. Kind of, I could have picked a better number than this, but this makes it a little difficult. So it's really 5 to the first. It's not 5 to the negative first. But anyway, plus 3. So 5 to the first is 5 plus 3 is 8. So negative 1 is going to give us an output of 8. So let's just plot these two numbers. 0, 4 is right here. Negative 1, 8. This is, again, going to be a really steep curve, but we can see that it does come out the direction we predicted based on knowing the translation rules. So there you go. So our domain is going to be negative infinity to infinity, or x such that x is equal to all real numbers. I don't know if you actually have to write it out all the way this way. I guess in set builder notation, you would have to write it this way. If you were writing an interval notation, you just say negative infinity to infinity. However, our range is y such that y is greater than 3, which was our horizontal asymptote, the blue dash line. So here's the answer for number 12. It's the 3. Well, I guess also this part is part of the answer as well. So we have the domain, range, and horizontal asymptote. All those 3 are the actual answers for this together. So there you go. Moving on to number 13, solve the equation. All right, well, we don't have the same bases here, so let's see if we can get that going for us. I know 625 is actually 5 to the 5 to the fourth, so 5x equals 5 to the fourth. Our bases are the same, so let's set the exponents to equal each other. Boom, you got x equals 4. Super easy on that one. Here's a one that's a little more difficult. Now I know 2 is a factor of 16, so 2 to the fourth is 16. So I've got 3x minus 5, and the bases are the same, the 2's. So I can set the exponents to equal each other. So that's going to be 3x minus 5 equals 4. Add 5 to both sides. We will get 9. Divide both sides by 3, and we're going to get x equals 3. Super straightforward on that one. However, number 15, they throw us a bit of a curveball. We've got all these bases that are totally different, but they all look like they have their prime factor is a 3. So 3 squared to the 2x power, and 3 to the fourth? No, 3 to the third. Oh, I almost went too far there. 3 to the third to the 3 minus x. Ooh, not 8. I'm getting ahead of myself here. Actually, 8's not anything part of this. Anyway, I don't know where that came from. Equals, all right, so we've got 9. So that's 9. That's 3 squared, 1 over 3 squared. But we can push that up to the top and make it 3 to the negative 2. So we've got 3 to the negative 2 here. So now our bases are all the same. I just need to clean up the exponents on the other side. So I've got 3 to the 4x times 3 to the 3 times the quantity 3 minus x. It's looking super ugly here, isn't it? Equals uh, 3 to the negative 2. Now all my bases are the same, so I'm just going to set the exponents. On this side, I need to add them together, and then they will equal 2. Oops, they're going to equal negative 2. But let's distribute this 3 here, so that's going to make this 9 minus 3x equals negative 2. Put the negative over here. So what I end up having here, I'm going to have x plus 9 equals negative 2. And then I am going to subtract 9 from both sides. So that means I'm going to have, oh yeah, there's supposed to be this. No, there's no 4 here. What am I thinking? I keep double checking my work here as I'm talking, and now I've lost my place. But yeah, this 4 isn't supposed to be here. We got rid of that with the negative 3x. Anyway, so I'm going to subtract 9 from both sides. So that means I'm going to have x equal negative 11. So that one's done. Kind of a little bit of a complicated one, but there you have it. We'll move on to number 16. Oh boy, here we go. Fractions. Well, 6, we can see this as 6 to the first on this part. We need to get the same bases, but 6 to the negative 1, we'll bring that to this, to the x equals, and then 6 to the second, or 6 squared, will give us equal bases. So we've got 6 to the negative x equals 6 squared. So negative x equals 2. Get that negative to the other side, we have x equals negative 2. All right, so 17, we need to find the domain of this function. So ln cannot equal a 0, or it can't be negative. So what I'm going to do here is I'm going to set this negative 3 minus x to equal 0 and find out where it's at 0. So we've got negative x is greater than, we want it to be greater than 3. Move that negative, and oh, we're dividing by a negative, so we switch this around. So x is less than negative 3. So here's our domain. It's x such that x is less than negative 3. And if we want, we can do a quick check just to make sure. We can just, let's substitute negative 3 into the equation here. So negative 3 minus a negative 3 is, why am I, oh, I put in 4 to make it 1. And then negative 3, let's try negative 10. That's going to be 7. So this works. So if I put in numbers that are smaller than negative 3, it comes out. All right, so for number 18, we have log 8, the function log 8, 4 minus x squared. But if we look at the 4 minus x squared, we can kind of tell that this is a parabola, because we have x squared, negative x squared plus 4. So we know it's a parabola that goes down. But since it's a log function, we can only look at values that are above the x-axis. So we're only looking at these parts. What I need to figure out are what these 2 points are. So what I am going to do is negative x squared, and that is greater than 4, or negative 4, sorry, because we're subtracting 4 from both sides. Then I'm doing something funky with the negative here, so I make negative x squared less than 4. And then x is going to really be equal to plus or minus 2. It kind of gets a little weird here, but I'm really just looking for these 2 points. So um, that was the method I found or used to get the 2 points, but that less than equal to thing, you just have to know that this has to be above the x-axis, so I'm looking for the stuff in between these 2 points. So x is such that negative 2 is less than x, which is less than 2. So that's really our domain here. Kind of a little tricksy one. This one, we're back to a fraction. So a log, again, must be positive. So I am going to look at a number line and figure out what's going to make this positive, right? So x minus 7, that's going to be my 7, and the x plus 5 is going to give me a negative 5. So I just need test values that are below this, in the middle, and above. So I'll use negative 6. Let's use negative, no, let's just use 0. 0 be easy. And then let's use 8. So let's just plug in negative 6 into the equation. And really, I don't need to solve this equation. I just need to know if I'm going to get a positive or negative value out of this. Still going to have negative 1 here, so it's a negative on top. Bottom, I'm definitely going to have a negative. So this is going to be a positive here. Substitute 0 in there. We'll have a positive on the top. We'll have negative on the bottom, so that's a negative. And then we'll substitute 8 in there, and that's going to give me a positive on the top and a positive on the bottom. So finish writing this out. Positive and positive, so that's obviously positive. So our domain on this guy is x such that x is less than negative 5 or x is greater than 7. This comma doesn't really look good, so I'll just write or in here. So that's our domain for number 19. All right. So here we want to graph the function, and this function is an ln function. So we know that ln of x would normally look like this guy going through 0, I'm sorry, 1, 0. So it normally look like this. But we've got like this negative 4 and stuff like that. So we're going to have a reflection, and really that's all we have here is this reflection that we need to concern ourselves with because of this negative 4 here. So our we should expect to have something that looks like this line instead. But what we want to do, just to get it a little bit closer to a sketch, is do some side work. So we'll do a x equals 2. We would put that into the original function, so negative 4 ln 2. Plug that all into a calculator, and we are going to get negative 2.77. Let's do one more function. We'll do 0. X is 0, and we'll plug that in. Oh, actually, no. Let's do x is 1, because we've already plotted that point on there. I don't think we can get x equals 0. Anyway, so negative 4, it would come out syntax error. And this does, in fact, come out to be 0, which is the point we had before. So we're going to plot these two guys. So we've already got 1, 0 plotted, so we just need to plot 2 and negative 2.77, which is almost exactly where I already guessed it. But this is our actual line right here. on the graph. So that one's kind of easy. It's kind of like a little bit of plug and play, but having an idea what it should look like helps you understand if you're going to get it right. Same thing here. Again, has to be bigger than 0. So I'm just going to reorganize this to be negative ln x minus 3. So we moved our horizontal line, or our axis by which it's going to reflect over, down to negative 3. So our original line would have normally gone through 1, 0, but now it's going to go through 1, negative 3 right there. And of course, it would look like this. However, we have that negative sign out in front here. So we should expect when we do some sort of side work that this is actually what we will see out of it. But let's just see if that's true. So x, y chart, we'll just do one value here. We'll do 2. We'll plug 2 into the formula or the function, negative ln of 2 minus 3. Plug all that into a calculator, and we get negative 3.69. So go over 2, come down 3, and then 0.69. Oh, I missed it by just a little bit. It's just a little bit above my sketch, my guessing sketch. And then of course this number is what we kind of moved it around against the 1, negative 3. So there's the graph for that guy. We'll move on to number 22. On this one, again, we can just reorganize this to be negative ln, the quantity x plus 4 plus 2. All right, so we have a couple things going on in this one. We have our plus 2, which means that the axis by which this is going to all kind of be on is now going to be involved with this plus 2 here. And normally, we would have had, the line would have passed through this point, which is 1, 0, but it's going to go up 2, so now it's up here at 1, 2. And this part means it's going to move to the left. The plus 4 means it's going to move to the left 4. So let's count over 4 places here. And that's where this line is going to pass through this. Now, of course, this asymptote over here, which used to be 0, also moved over 4 places the same direction, so it moved to the left. So this is our vertical asymptote right here that our line is going to go against. Now, we have this reflection because of the negative ln right here. So instead of increasing, it's going to be decreasing. So it's going to go through our negative 3, 2, and it's going to be something like this, or at least decreasing. But we'll do the side work. Let's just put in 0 here, because 0 is going to make that ln of 4. But I'll write it all out here. So negative ln of 4 plus 2. Plug that all into the old calculator, and we get 0.614. Oh my gosh, this is way higher than what I had put here. But anyway, so we got 0 and 0.614 is right here. So our line is descending. It just doesn't decay exactly how I had guessed it would, but it is decaying. So anyway, I don't know if you call it decaying or getting smaller or whatever. As it goes to infinity, it's the y value is getting smaller and smaller and smaller. Uh, anyway, so there's 22. Let's go on to 23. We need to solve these logs, solve these equations. Now we have log 6. We move it through here, and that picks that -1 up as an exponent. And then we set that to equal the quantity here, so x plus 2. So a little bit of a cycle there. Now 6 to the -1 is actually 1/6 equals x plus 2. Subtract 2 from both sides. And we're going to have to find a common denominator here, which is going to end up being 1/6 minus 12 over 6 equals x. And then, of course, 1/6 minus 12 is going to be -11 over 6. Can't reduce that. Equals x. Now, when we do this, yeah, it's pretty yucky. But when we do this, we have to check, because there's sometimes some funny things that can go on that we get an erroneous result here. So we have log 6, the quantity -11 over 6, plugging that in for x, plus 2. That equals -1. Find the common denominators on the inside here, plus, we already found this, it's 12 over 6 equals -1. So, of course, log 6, and the inside here is going to end up equaling 1/6, shocker, -1, or equals -1. And then that 6 in exponent form is really going to be 6 to the -1. And then if we did that cycle thing where we take the log number, the base, it's going to get 6 to equal -1, and then 6 to the exponent of -1. So they equal. Check-a-rooney. So yucky. Logs are not my strong suit, but I'm going to try and struggle through these 10 more questions after this one. So we got 24 here. We'll do that same cyclic thing. So 5 to the first, which is really just 5, I know, but I'm just trying to get the habit of doing the putting that as an exponent, because it could be 3, it could be 4, but here it's 1. So now we can make this into a quadratic. So now we've got, let's see, we're going to have x minus something, x plus something. It's going to be, what is it going to be? 5 and 1, duh. Okay, so here we have x is equal to 5 and x is equal to -1. So we've got these two values, but we have to check them. So we're going to check -1 first. So I will put -1 into the original log. So log 5 times the quantity -1 squared minus 4 times -1, all equals 1. Well, the inside reduces to 1 minus a -4, which is actually 1 plus 4 equals 1. Now I'm going to log 5, and then 5 inside is equal to 1. We should see at this point that it's going to work, but we'll pick up that as its exponent, and then we see 5 is equal to 5 to the first, but that just means it's 5 of 5. That checks out. Now we have to check the 5. To check the 5, we are going to do log 5, and then 5 squared. I guess I didn't need to put brackets here because it wasn't a negative, but anyway, 5 squared minus 4 times 5 is equal to 1. 5 squared is obviously 25, and 4 times 5 is 20, and so that's going to end up equaling 5. And we're kind of right back in the same boat we were at on the check for -1, but just walk us right through this again. 5 is equal to 5. This one checks out. So both values I ended up checking out. So our answers to this are x equals 5 and x equals -1, just like we had before. Let me square this one as well. Forgot to put my box. All right, number 25. Oh, now we got log 42. It's a big number. Oh my gosh. Run and hide. It's scary. So 42 to the first is equal to x squared minus x. Well, this is how I did that again. I just picked up that as the exponent. This is a quadratic, so 0 is equal to x squared minus x minus 42. Holy smokes. What? It's going to be x minus something and x plus something. It's 7 times 6 give us 42. X minus 7. Yeah, yeah, 7 and 6, that's going to give us 1. So, and 7 times 6 is 42. Yeah, 36 plus 6 is 42. Yep. So 7 and 6 are hard numbers. How exciting. So x is equal to 7 and x is equal to -6. So here we go. We're going to check -6 first. These have a lot of extra work, but so put the -6 back into the original equation and log 42 and then -6 squared minus a -6 is equal to 1. We're going to get 36 minus, or actually plus 6 because minus a minus equals 1. This is obviously log 42. Log 42 of 42 equal to 1. We should see that this is going to work out. But 42 picks up that 1, and we end up with 42 with equals 42 to the first. So yes, it checks. All right, so let's check 7. We'll put it into the original equation or function. So we have log 42, and then 7 squared minus 7 equals 1. So that's 49 minus 7. I can already see that's going to be 42, which puts us right back in the same boat that we were at before with the -6. But just to write it all out, I suppose, log 42 of 42 equals 1, and then that picks up it as a negative or as a exponent. So we see that this checks as well. Writing down all your work can get you more points, or at least most of the points. If you make a mistake, our instructor at least gives you some points for doing the work. And if you get the answer wrong, you will see where you got it wrong, but see that you continued on a path of using it. So these next ones we have to write as the sum or difference of logarithms. So we have to note here. Remember in class, this is something that I never learned until class the other day. So I'm just going to write them down here to remind myself. So log sub a number divided by a number is equal to log sub a m minus log sub a n. Now, order is important here, of course. You subtract the bottom from the top. But for the multiplication, you end up with log sub a m plus log sub a n. And that one you can transpose them back and forth. It doesn't matter because it's addition, but anyway. And then log sub a m to the r is also equal to r log sub a m. So these 3 bits of information here are what we're going to use to sort out this problem. So since it's a division problem, we're going to use a subtraction, right? So we're going to rewrite this as a subtraction problem. So we're going to end up with log sub 4 x to the 6th and minus log sub 4 x to the 3rd. No, I don't know why I put brackets there. I didn't need to, but this 3 actually, because of the note we made before, can actually be written out in front of the log. So we get log sub 4 times the quantity x plus 6 minus 3 log sub 4x. And there you go. There is our final answer for number 26. Number 27 is exactly the same, except we have 11x on the top. So that's going to end up giving us something else. So we have log sub w times 11x minus log sub w 4. But since we have 11x, that's a multiplication, so we can split that out a little bit further into an addition. So we'll have log sub w 11 plus log sub w x. I should make these cursive L's because they look too much like ones. But anyway, x minus the log sub w 4. So there you go. That is that one converted. And this one is trying to throw us for a little loop, giving us a radical inside there. Remember, this is actually a squared, it's 2. We don't write the 2 because we assume it. So this can be rewritten as x, or 6x to the half power, or exponent of 1/2. So that gets rid of that radical inside. So we have log sub 3 times this. Well, this can be split out into, remember we can move this 1/2 out front. So we can rewrite this as half log sub 3 times the quantity, or times 6x, right? But since this is 6 times x, we can split that out into addition. So we have 1/2 times this quantity log sub 3 6 plus log sub 3 x. All right, so now we can distribute this 1/2 across to these two. So we have half log sub 3 6 plus half log sub 3 x. So that's that guy. So we're basically just splitting this out into subtraction or addition. Expressed as a single logarithm. All right, so now we're going to do exactly what we did before, except we're going to do it in reverse. But one thing to note here is pluses go on the top and minuses go on the bottom. So when we have some minuses in there, we know that we're going to have some sort of fraction. So we need to make sure that we put them in the right places. So the pluses go on top and minuses go on the bottom. So make this look like a fraction. So just as a reminder, that's how this is going to work. So remember, this 6 out in front is actually the exponent of, notice also we all have all the same bases here, the a, but this 6 is the exponent of m, the negative 3/5 exponent of the n, and the 1/4 is the exponent of the j, and the negative 5 is the exponent of the k. So we've got m6, because it was a positive, it's going to go on the top. We have n to the negative 3/5, it's going to be on the bottom. So I'll put my fraction bar here. The j is to the 1/4, and the k is to the negative 5th. So we'll put k to the negative 5th. My fraction bar is a little long here. Let's make it the right length. All right. So that is that. So logs sub a uh, times that quantity, and so that's our answer for that guy. We'll move on to number 30. Now this one's pretty easy because it's just a plus, so it's really going to turn it into a multiplication. So we have to put our exponents to our groups here. So log sub 6 x to the third plus log sub 6 times the quantity x minus 6 to the fifth. Oh boy. So remember, these become the exponents of whatever's after the log. Now to express this as a single log, we have log sub 6 times the quantity x times the quantity x minus 6 to the fifth, and then close this bracket. And so that's written as a single log for number 30. Number 31, another problem just the same as the first, or same as the previous. We're going to distribute our exponents here, put those in here. But this is a 2. It's not the same base as the rest. So we could actually rewrite this as log A. I'm trying to think how we do this. Is this just log A2? Let me just write out this other part and come back to that part. So log A times the quantity 2x plus 1 cubed minus log A times the quantity 2x minus 1, and that's squared, plus log A2. I don't think that's technically how that works. I think that 2, let me see. Log A of A would be 1. I think this is A, log A of A. And that 2 is technically the exponent of A. So this A of A would be 1. So we wouldn't put the 1 here. So really this is going to be, that 2 is going to become the exponent of the A. I think technically that's how this should work. But like I said, logs are not my strong suit. So if you're confused about this one, I'm sure I'm going to ask my professor about it. But I'm going to write this as this way. So there you go. Now, since we have a negative and positive, we're going to have a fraction bar. So remember, the things that are negative are going to go on the bottom. Positives are going to go on the top. So we've got the quantity 2x plus 1 cubed times the a squared, and then we have minus this log, so this is going to be the 2x minus 2 squared. And this is log a, of course, equals, no, not equals. Oh my gosh, I'm getting out of control here. This is log a times this mess. Probably didn't explain that one the best. Obviously, I have a question myself, so I'm going to check with Professor Lamp. If you guys have some other way to solve that one, just put it down in the comments. All right, so we are going to solve these equations. Notice that we have this log 5 base is the same. So really we can just take 2x plus 4 is equal to 2x plus 7. So the 2 x's are just going to go away, and then 4 equals 7. Nope, doesn't happen. So this one, pretty easy. There's no solution. We would have seen that earlier, 2x plus 4. whatever. Anyway, moving on 31, or 33, sorry. Here we have the bases are the same on this side. But we want to condense this to log sub 3 times the quantity x times the quantity x minus 24, and all of that is equal to 4. Now we can take the 3 and pick up the 4 as the exponent, or actually I'll distribute first, so I have x squared minus 24x log 3, and that all equals 4. Okay, so now I can take the 3 and pick up the 4 as my exponent and set that equal to the quantity of x squared minus 24. Well, x to the fourth is, I should know these, memorize them, but I'm going to have to do it by hand. That's 9, that's 27, 27 times 9 is 81, I think. Yeah, 81. So 81 is equal to x squared minus 24x. Don't need the parentheses, so I don't know why I drew them before. I'm parenthesis happy. So this turns into a quadratic again. So we're going to have x squared minus 24x minus 81. It's a really big quadratic number. We're used to nice simple ones, so this one's kind of big. But we've got x is going to be x minus something and then x plus something. So just write those down. What are my numbers going to be? Well, 27 and 3 get me 81, so it's probably going to be those. Yeah, 27 plus a 3, that would give 24. Yeah, so negative 24. Yep, so that's it. So x is equal to 27 and x is equal to negative 3. However, we need to check these dudes. So let's check the negative 3 first. So we're going to put negative 3 into our function, or our logarithm. So we have log 3, negative 3, plus log 3, negative 3 minus 24. And all of that equals 4. Well, we cannot have negatives in these logs. So it can't be a negative. Negative? No, negative. So there's no solution for this. So this is an example of why we have to check to make sure that it is an actual solution. So negative 3 is not a solution. So now we're going to check 27. So we have log 27, which, ooh, it's positive, plus log sub 3, quantity 27 minus 24, which is going to result in a positive as well. It's going to be 3 in there. So, and all that equals 4. So this is log sub 3, which is going to be 3 equals 4. And this over here is going to be log sub 3. And it's going to be 3 to the third, 3 cubed. And then, of course, they're going to be, this is plus in the middle here. These are all the same. So we've got 3, and that's going to be a 1. 3 plus 1 is 4. And, of course, 3 plus 1 is 4. So 27 works out. So there you go. There's number 33. 34. Oh my gosh, hold on to your butts. These spaces do not match. Oh no! What do we do? Well, let's see if we can get the log 8 times the quantity 3x to have a base of 2. So we set log 8 3x to equal y. Now that 8 can pick up y as an exponent and equals 3x. This can be set as 2 to the third to the y equals 3x. Now we have 2 to the 3y equals 3x. And then, of course, we can turn this back into a log. So log 2, 3x is equal to 3y. Now we can take that 3 and divide that other side, or make it 1/3 log 2 and 3x. So there you go. We've got now our base with a log 2, which is what we had on the other side. And we also have that 1/3 out in front as well. So this might make this pretty easy now. So we have 1/3 log 2, x plus 6 is equal to 1/3 log 2, 3x. All right. So what do we do? Yeah, this is where I pulled that from. The work we did before, we pulled that out and replaced it over here. We have our logs are equal. So we really have x plus 6 equals 3x. Well, we are going to get the x's on the same side, and we end up with 3 equals x. Move this over here so we can do our little check work. We got to check the 3 to make sure it actually works. So I'm just going to put it into our revised logarithm. So 1/3 log 2, 3 plus 3 equals 1/3 log 2, 3 times 3. Oh, wait, not 3 plus 3. 3 plus 6. What am I thinking? There we go. So equals 1/3 log 2, and then it's 3 times 3. There we go. So this is going to be 9. This is going to be 9 in here. So everything's going to match, but I'll write it out. 1/3 log 2, 9 equals 1/3 log 2, 9. So x is, in fact, our answer. Or sorry, 3 is our answer for x. Oh my gosh. Too much math for the day. So that's number 34. I know there were 35 problems on our exam or our review, but 35 is not going to be on the actual exam according to our professor. So there you have it. Good luck. Um, if you have any questions, please, just write them in the comments or ask me in class. Hit like, subscribe, all that kind of stuff, so you can get the next video for chapters 6 and 7, I think. And we'll see you in class, and hope you do well on the tests. See ya.